Antarctica is the coldest place on Earth, covered by a thick blanket of ice that has existed for millions of years. Because of this, many people think of Antarctica as unchanging and permanent. For a long time, scientists also believed that much of Antarctica, especially East Antarctica, was very stable and unlikely to change quickly. However, new scientific research has shown that this belief is not fully true. Evidence now shows that a large part of Antarctica collapsed very rapidly about 9,000 years ago, during a time when Earth's climate was warm in a way that is similar to today. This discovery is important because Antarctica holds an enormous amount of ice. If large parts of this ice melt and flow into the ocean, sea levels around the world will rise. Rising sea levels affect coastal cities, islands, farmland, drinking water, and millions of people. By studying what happened thousands of years ago, scientists are trying to understand what might happen in the future as Earth continues to warm due to human activities. Antarctica contains the largest amount of frozen water on the planet. All the ice in Antarctica combined holds enough water to raise global sea levels by about 190 feet if it were to melt completely. While scientists do not believe all of this ice will melt anytime soon, even a small percentage melting could cause serious problems. A rise of just a few feet in sea level would flood many coastal cities, damage ports, destroy homes, and force millions of people to move. For many years, scientists believed that East Antarctica was safer than other regions. This is because much of its ice rests on land that is above sea level, which makes it harder for warm ocean water to reach and melt the ice. In contrast, West Antarctica has ice that sits below sea level and is known to be more unstable. Because of this difference, East Antarctica was often considered stable and slow to change. The new research challenges this idea. Scientists have discovered that around 9,000 years ago, part of East Antarctica lost ice very quickly. This happened during a natural warm period known as the early Holocene, which followed the last ice age. During this time, global temperatures were slightly warmer than today in some regions. The collapse happened not because of sudden warming in the air, but because of changes in the ocean around Antarctica. The collapse occurred in a region known as Dronning Maud Land, which is part of the East Antarctic ice sheet. Large floating ice shelves in this area broke apart, allowing land-based ice to flow rapidly into the ocean. This process raised sea levels and permanently changed the shape of the Antarctic coastline. The speed of this collapse surprised scientists, as it showed that even very large ice sheets can respond quickly once certain conditions are met. To understand events that happened thousands of years ago, scientists cannot rely on photographs or written records. Instead, they study natural evidence preserved in the environment. In this case, researchers collected sediment cores from the seafloor near Antarctica. These sediment cores are long tubes of mud that have built up layer by layer over thousands of years. Each layer of sediment contains tiny clues about the environment at the time it was formed. Scientists examined microscopic marine fossils, chemical elements, and rare isotopes found in these layers. By measuring these materials, they were able to determine when ice shelves existed, when they collapsed, and how ocean conditions changed over time. This detailed analysis allowed researchers to pinpoint the collapse to around 9,000 years ago. One of the most important findings of the study is that warm ocean water played a major role in the collapse. This water is known as circumpolar deep water. It flows deep below the ocean surface and circles Antarctica continuously. Although it is only slightly warmer than freezing, this water carries enough heat to melt ice when it comes into contact with it. Around 9,000 years ago, changes in ocean circulation allowed this warm, deep water to move closer to the Antarctic coast. It flowed onto the continental shelf and reached the underside of floating ice shelves. Ice shelves are thick platforms of ice that extend from the land out over the ocean. When warm water flows beneath them, it melts them from below, making them thinner and weaker. Ice shelves play a crucial role in controlling how fast ice moves from land into the ocean. They act like giant braces or supports that slow down glaciers behind them. When ice shelves are strong and intact, they hold back land ice and reduce the amount of ice flowing into the sea. When ice shelves thin or collapse, they lose their ability to support the ice behind them. As a result, inland glaciers speed up and push more ice into the ocean. This does not happen gradually over thousands of years. Once ice shelves are lost, the response of land ice can be rapid, leading to sudden increases in ice loss and sea level rise. The research also revealed a dangerous feedback loop that helped speed up the collapse. As ice melted, it released fresh water into the ocean. Fresh water is lighter than salty ocean water, so it stays near the surface. This created layers in the ocean, with lighter water on top and heavier, warmer water below. Because of this layering, the surface water could not mix easily with deeper water. This trapped the warm, deep water near the ice shelves, allowing it to continue melting ice from below. As more ice melted, more fresh water entered the ocean, strengthening the layering even further. This feedback loop caused ice loss to accelerate instead of slowing down. Several local factors made the collapse in Dronning Land especially fast. One important factor was the shape of the seafloor. Scientists discovered a deep underwater valley that acted like a channel, guiding warm, deep water directly toward the ice shelves. This made it easier for heat to reach the ice. Another factor was changes in sea level caused by the loss of ice. As ice melted and moved into the ocean, the weight on the land decreased. This allowed the Earth's crust to slowly rise, a process known as glacial rebound. This temporarily raised local sea levels along the coast, allowing ice to float more easily and enabling warm water to reach farther beneath the ice shelves. The conditions that caused the collapse 9,000 years ago are not just ancient history. Scientists are now observing similar processes happening around Antarctica today. Ocean temperatures are rising as the planet warms, and warm, deep water is reaching areas it could not reach before. In West Antarctica, glaciers such as Thwaites Glacier are already thinning rapidly due to warm water melting them from below. This glacier is often called the Doomsday Glacier because of its potential to raise sea levels significantly if it collapses. Similar patterns are being observed in nearby glaciers as well. For many years, East Antarctica was considered the safest part of the continent. However, new satellite measurements and gravity data show that some areas of East Antarctica are already losing ice. Glaciers such as Totten and Denman are showing signs of thinning and retreat. The ancient collapse shows that even ice sitting on land above sea level can retreat quickly if warm water finds a pathway underneath it. Hidden channels beneath the ice can allow warm water to reach grounding zones, where ice meets land. Once this happens, melting can accelerate rapidly. A powerful ocean current known as the Antarctic Circumpolar Current flows around Antarctica from west to east. This current helps move heat and fresh water around the Southern Ocean. During the ancient collapse, meltwater from Antarctica changed the density of ocean water, affecting how this current behaved. Climate models suggest that fresh water from melting ice can weaken ocean mixing and steer warm water toward the Antarctic coast. Modern observations show that similar changes may already be happening. This raises concern that warm water could increasingly reach East Antarctica, triggering faster ice loss. If East Antarctica were to lose ice at rates similar to those seen 9,000 years ago, sea levels could rise much faster than current predictions suggest. Even a rise of 2 or 3 feet would have serious consequences for many parts of the world. Coastal flooding would become more common, even on calm days with no storms. Storm surges would become more destructive, pushing water farther inland. Salt water could contaminate drinking water supplies and farmland. Low-lying island nations could become uninhabitable, forcing entire populations to relocate. Ice sheets respond slowly at first, but once certain thresholds are crossed, change can become rapid and difficult to stop. The ancient collapse shows that ice systems do not always change gradually. Instead, they can remain stable for long periods and then suddenly retreat very quickly. Because ice sheets operate on timescales longer than human lifetimes, decisions made today will affect the planet for thousands of years. Once ice is lost, it takes a very long time to rebuild, even if temperatures later cool. The study of ancient sediments has given scientists a clearer picture of how Antarctica behaves under warming conditions. It shows that ocean heat is just as important as air temperature in driving ice loss. It also highlights the role of meltwater feedbacks in accelerating change. Some ice sheet models used today do not fully include these feedback processes. This means they may underestimate how quickly ice shelves can break apart and how fast sea levels could rise. Improving these models is critical for making accurate predictions about the future. The layers of sediment beneath Antarctic waters tell a powerful story. They show that when warm ocean water and meltwater work together, ice systems can collapse suddenly and dramatically. This happened once before, long before human civilization existed. Today, human-caused greenhouse gas emissions are warming the planet and the oceans at an unprecedented rate. While the exact future is uncertain, the past shows that Antarctica is capable of rapid change under the right conditions. The ancient collapse of Antarctica reminds us that Earth's climate system has tipping points. Once crossed, these tipping points can lead to changes that are difficult or impossible to reverse on human timescales. Reducing greenhouse gas emissions, limiting ocean warming, and carefully monitoring Antarctica are critical steps for the future. The decisions made in the coming decades will shape coastlines, ecosystems, and human societies for many generations. In simple, Antarctica collapsed before when the ocean warmed. The collapse happened faster than expected and raised sea levels. Similar ocean conditions are developing today. This does not mean disaster is guaranteed, but it does mean the risk is real. By learning from the past, scientists are trying to understand how to protect the future. The story of Antarctica 9,000 years ago is not just about ice. It is about how closely connected the Earth's systems are, and how small changes can sometimes lead to very big consequences.